in logic, we analyze statements and compound statements to see whether they're true or false, or under what conditions are they true or false. So over here on the bottom, I have three statements. One of them is 1 plus 1 equals 2. I'm going to abbreviate that with the variable p. The second statement is a triangle has three sides. I'll abbreviate that with the variable q. And the third statement, a square has three sides, and I'm abbreviating that with the variable r. So two of these statements are true, and one of the statements is false. I think I want to throw in a fourth statement that's also false. Let's say a square has five sides is also false. Now we can create more complicated statements that in some ways combine simpler statements like these four. So for instance, I could say, make a sentence like this: P and Q, which is a symbol for and, which is this upside down V. Now that statement, which is now 1 plus 1 equals 2 and a triangle has three sides, since both of those things are true, P and Q, that statement is also true. But if I try to say P and R, although it's true that 1 plus 1 equals 2, the second part is not true. It's not true that the square has three sides. And even though this is sort of a partially true statement, we don't get to say that in this type of math. So it is false. P and R is a false statement. It's not true that both 1 plus 1 equals 2 and that a square has three sides. And if I say something like R and S, square has three sides and a square has five sides, neither of those things are true, so of course the whole thing is false. And that's how what's called conjunctions work. That's what fancy word is for and, is conjunction. Now you can organize this information into something called a truth table. And what a truth table is, if there's two like simple statements like P and Q, the truth statement has 4 rows. True, true, false, false, and then the second column I go true, false, true, false. This gets me every combination of true and false. So conjunction is true when both things are true, but if there's any falses, the conjunction is false. Now we're going to look at what happens with OR, and I'm going to erase this stuff on the side here. So if I say something like P or R, 1 plus 1 equals 2, or a square has three sides, if either of them are true, the statement is true. If both of them are false, like R or S, square has three sides or a square has five sides, both of those are false, so the entire, these are called disjunctions. The entire disjunction is false if both things are false. But one thing that's a little unusual, like because it sort of is different from what happens in just regular like English language, if you say two things that are true with the word or, like 1 plus 1 equals 2, or a triangle has three sides, if both things are true, the or statement is true. The or doesn't mean like only one or the other. Both things being true makes the or statement true also. So that's a little bit unusual. Here's the truth table. Okay, it's going to have the same 4 rows. But for this one, only this is false, while the other ones are all true, including the one that's where they're both true. Now, the third thing on this list is something called XOR. And I'm going to erase this stuff on the side, explain what that is. XOR also stands for exclusive OR. So, and that's usually in like the English language how we use regular OR. So if I say P XOR R, 1 plus 1 equals 2, or a square has 3 sides, that's going to be true because exactly one of the things is true. And if I say a square has 3 sides, XOR a square has 4 sides, that's going to be false because neither of them are true. But if I say 1 plus 1 equals 2, XOR a triangle has 3 sides, those things are both true, but that means that means that the entire statement is false because XOR is only true if just one of the things is true, not if both. So again, I can make a truth table for this. TTFF, TFTF. So exclusive OR is true when just one is true, and if both are false, or if both are true, it is false. So these are the 3 truth tables for this lesson. So here on the left, I have the truth table for P and Q. Now, that truth table could be for other letters also. In this situation, so this is where P and Q or P, where either of them might be true or false. But once we actually set up what P and Q actually are, like in this case, they're both true. So in that situation, we'd be looking at this line of the truth table. Now another symbol in this kind of logic is, it looks like this, or sometimes people make it look like that, like a tilde, like in Spanish. And that you put in front of a variable. So we would call this not P. And if we're using the P from over here, not P would be, not P would be 1 plus 1, does not equal 2. It's sort of the opposite. Now, in this case, P, 1 plus 1 equals 2 is true. So not P, 1 plus 1 does not equal 2, will have the opposite truth value, which is false. R, square has 5 sides, is false. But not R, which is a square does not have 5 sides, is true. So the negation has the opposite truth value. Okay, the last part of this video is to show you how we could use these truth tables to find the truth of certain compound statements, that have an AND or an OR or an XOR. Normally, if I say something like, is not T and V, is that true or false? Well, we know nothing about, maybe I shouldn't use T because that looks like true. So why don't I say not V and let's say U. Now we don't know if that's true or false because we know nothing about V and U. If I tell you with the word given V is a fancy way of saying V is true. And if I say given U, that's a fancy way of saying U is true. So then, if I know all that, I can find the truth value of this sentence, because not V, since V was given as true, not V is false. And U was given as true, but false and true is false, because they have to both be true for the and to be true. Here's another example. You could also be given other information. Let's go back to, I'll use, these P's and Q's are not related to these ones. In fact, I'll use different letters, U, V, I'll say W and Y. Given that not W, that's a fancy way of saying that not W is true. That's a fancy way of saying that W is false. And also given, let's say, Y, which is that Y is true. So now I can ask questions about these things, like I can say, what is W or Y? Well, it might help you to say, okay, because not W was given as true, W is false. And since Y was given as true, I wrote and, but I was thinking of saying or, so let me just switch that. And false or true, as long as one of them, at least one is true, the whole thing is true. And just to give another example with the same given, if it was not W, let's just say XOR, not Y. So again, since not W is given, not W is true. And since Y was given as true, not Y is false. And true XOR false, if exactly one of them is true, the whole thing is true. So if you are told about the truth value of two, little statements, including sometimes where they tell you that something's false by telling you that the negation of it is true, we can use that to find the truth value of these compound statements that involve and or XOR. Okay, and that's going to be this first or this lesson about negation, or, and, XOR, and about identifying, using truth tables to find truth values of compound sentences that involve multiple statements with connectives like or, and, or XOR.